What's up, guys? It's me, Sir Ernest, and today we will have an example related to the Euler-Lagrange equation. The problem reads: consider the case of a projectile motion under gravity in two dimensions, as was discussed in example 2.6 of our textbook. Find the equations of motion in both Cartesian and polar coordinates. Okay, so let's set up first our illustration. So again, we're going to consider a two-dimensional coordinate system x and y. So this is x and y, and let's say the particle left, or the projectile left the origin, and it was projected, let's say, up to a certain point. Okay, let's consider, let's say, this path. This is your projectile. Let's say we consider an arbitrary point somewhere here. Okay, so this arbitrary point is where your particle is of mass m, and it has coordinates x and y. Now, excuse me. So this x and y can be identified as such. So this is your x, and sorry about this. And this is your y. Okay, so now if we're going to compare this to our polar coordinates, we have this will be our r, and this will be our theta component. Okay, so here we note that the velocity of the particle at this point is this, which can be expressed as a vector sum of the x component, velocity of the x component, and the velocity in the y component. So this tells us that the speed of the particle squared by Pythagorean theorem will be x dot squared plus y dot squared. Okay, so we already know that in Cartesian coordinate system, the kinetic and potential energy are given as follows. That's 1/2 m times x dot squared times y dot squared, and potential energy is equal to mg y. And therefore, the Lagrangian becomes 1/2 m x dot squared plus y dot squared minus mgy. Okay, so as you will notice again, this Lagrangian is a function of x dot, y dot, and these three variables are functions of time. And this tells us that this has 2 degrees of freedom. That means we have two Euler equations, or Euler-Lagrange equations. First Euler-Lagrange equation is in x. So this is derivative of the Lagrangian with respect to x minus derivative with respect to time of the derivative of the Lagrangian with respect to x dot, and this is equal to 0. So applying this, we have 0. This is 0 because, again, as you will notice here, the Lagrangian is not an explicit function of x, minus the total derivative with respect to time of this derivative. So this is derivative with respect to x dot. So this one. So this is m x dot equals 0. So this gives us that m is constant. So we can cancel it because this is equal to 0. So the total derivative with respect to time of x dot is x double dot. So the acceleration in the x component is equal to 0, which is what we already know using Newton's laws of motion. Now, for the y component, we do the same. Sorry, it should be partial derivative with respect to y. Minus total derivative with respect to time of partial derivative with respect to y dot. And this is equal to 0. In this case, this term is not 0 because the function depends on y as well. So this is equal to derivative of L with respect to y is negative mg. And then minus total derivative with respect to time of my dot. And this is equal to 0. So you will notice here that we can already cancel m because m is a constant. Then we'll end up with our usual equation of motion along the y, which is y double dot is equal to negative g. Okay, so you will notice that this is the exact acceleration components as you have learned in your general physics. Now let's compute for let's determine the coordinate, the equation of motion along the along the polar coordinate system. Okay, so here we're going to use the conversion of polar coordinate and Cartesian coordinate system. Okay, so we already know that. Sorry, I just want to make this straight. Okay, here. Okay, so we know that the x component is equal to r. So this is x, so this is r cosine theta, and y is equal to r sine theta. So from here, we can actually calculate the velocity functions x dot and y dot. X dot, here we cannot assume the r changes as the particle moves in the trajectory as well as theta. So that means r and theta are both functions of time. So that means the total time, the time derivative of x in terms of the polar coordinates should use your usual product rule. So this is equal to r dot cosine theta minus r theta dot sine theta. And your y dot would follow the same routine. So that's r dot sine theta plus r theta dot cosine theta. Okay, so therefore the velocity squared, v squared, is now equal to square of this plus square of this. Okay, so let's do the algebra. So square of this, so that's r dot squared cosine squared theta minus 2r r dot theta dot cosine theta sine theta plus r squared theta dot squared sine squared theta. So this is equal to x dot squared here or here. Okay, then plus square of this. So this is r dot squared sine squared theta plus 2 r dot theta dot cosine theta sine theta plus sorry, r squared theta dot squared sine squared theta. So from here, it's very clear that we can cancel the middle terms and this term. Okay. Also, this term can be combined with this term, and this term can be combined with this term. So the end result of v squared is just equal to a very simple binomial, r dot squared plus r squared theta dot squared. So therefore, the Lagrangian will now be equal to 1/2 m times r dot squared plus r squared theta dot squared minus mg y, where y is this one. So this is minus mg r sine theta. And as you will notice, the Lagrangian in polar coordinate is a function of r dot, theta, theta dot, and those are functions of r. So here we have 2 degrees of freedom, so that means we will have 2 Euler-Lagrange equations. Okay, so let's calculate the equation of motion, Euler-Lagrange equation in r and theta. So r, okay, so partial derivative of L with respect to r minus total derivative with respect to time of partial derivative of L with respect to r dot equal to 0. So this is now equal to, again, taking note that r and theta dot, r dot and theta are all functions of time. Okay, so there will be terms that you will use product rule and chain rule, so please be careful with that. Okay, so this is now can be written in like this. So this is m r theta dot squared minus mg sine theta. So this is the derivative of L with respect to r. So this is r and this is r. Minus total derivative with respect to time of m r squared theta dot. And this is equal to 0. Okay, simplifying this, again, m will cancel. So m is constant and common to all terms. So we'll end up with this term becomes r squared. I'm sorry about that. This should be, okay, They should be, sorry, they should be, okay, look at the wrong variable. So this is r dot, sorry. My apologies. This r dot. But again, m will still cancel. Okay, so now we can rewrite this as, this is r double dot equals r theta dot squared minus g sine theta. Okay, then lastly, for theta, we do the same. So this is derivative with respect to theta minus total derivative with respect to time of L, derivative of L with respect to theta dot equals 0. And then, so this becomes derivative of L with respect to theta. So this is the only term that has theta here. So this is negative mgr cosine theta. Then minus the time derivative with respect to theta dot, which is this term. So this is mr squared theta dot, and then this is equal to 0. So again, m will cancel and one of the r's will cancel. So sorry, we should not cancel the r. Sorry about that, because r again is a function of time. So it's not constant, so we cannot cancel it here. But we can but we can rewrite this as negative gr cosine theta minus, again, product rule, then chain rule. So this is negative 2 r dot theta dot minus r squared theta double dot. And then this is equal to 0, which gives us theta double dot equals negative of g cosine theta plus 2 r dot theta dot over r. Okay, so this is the equation of motion. And then of course, it's easy to determine the position and the velocity functions from the acceleration functions. As you will notice, the result shows that it's clear that using the coordinate system is simpler than the polar coordinate system. Hence, we use it to solve the problem. So remember that in the Cartesian coordinate system, the equation of motion is simply x double dot equals 0 and y double dot is equal to negative g, which is very much simpler, or much simpler than these two equations of motion. Okay, so just that's why whenever we solve using Newton's laws involving projectile motion, we just simply use the Cartesian coordinate system. Okay, now as you will notice also that when we calculated or determined the Lagrangian in the Cartesian coordinate system, this Lagrangian is a function of x dot, y, and y dot. So you will notice that the dependencies in Cartesian coordinate system is less than the dependencies to the coordinate system in the L. So that's why we could expect this a simple result from the start. Again, because the Lagrangian is only an explicit function of three variables. Whereas in polar coordinate system, you can see that the Lagrangian is a function of four variables. Okay, so I hope this is clear. Okay, don't forget to, if you have questions, please do not hesitate to contact me through my official channels. In the meantime, this ends our solution to problem 7.3, and I hope you learned something in this video. Thank you for watching. Then I'll see you again in the next video. Bye-bye.